The paper explores the application of pre-trained convolutional neural networks, CNNs, and vision transformers, ViTs, for periocular recognition. It leverages the success of these architectures in various computer vision tasks, demonstrating their suitability for recognizing individuals based on periocular images. The periocular region offers a balance between using the iris and the face for biometric recognition, making it ideal for non-cooperative biometrics due to its flexibility and minimal acquisition constraints. The authors employed transfer learning, specifically one-shot learning, to tackle data scarcity. They compared 3 CNNs and 3 ViTs with varying depths and parameters, analyzing the impact of network complexity on recognition accuracy. Additionally, they explored different methods to normalize layer representations and demonstrate the benefit of combining CNN and ViT descriptors, as well as traditional handcrafted features, such as local binary patterns, histogram of oriented gradients, and scale-invariant feature transform keypoints. The authors also introduce a new approach to comparing left and right eye images by flipping one eye's image horizontally to align the orientations and shapes of the overall eye structure. This approach makes the recognition task more realistic and challenging. The authors propose a methodology for extracting periocular features from convolutional neural networks, CNNs, and vision transformers, ViTs. They utilize 3 CNNs, R18, R50, and R101, and 3 ViTs, tiny, small, and base, with varying parameters and depths to extract features from periocular images. The features are extracted from intermediate layers of each pre-trained model, resulting in 3D tensors for CNNs and 2D tensors for ViTs. The parameters of each model are detailed in Table I, including the number of convolutional layers, activation channels, and embedding sizes. Features are extracted from all layers, excluding the last layers, which typically involve global average pooling or fully connected layers. The extracted features are compared pairwise using cosine similarity, a common method in biometrics. 5 normalization methods are evaluated for computing cosine similarity: L2 normalization per patch, per channel, of the entire vector, averaging across channels, and averaging across patches. In addition to CNN and ViT features, 3 traditional handcrafted feature methods are employed as baselines: local binary patterns, LBP, histogram of oriented gradients, HOG, and scale-invariant feature transform, SIFT. These features are extracted from non-overlapping regions of the image and compared using distance metrics. The UBIPR periocular database is used, containing 1,718 frontal view images from 86 individuals, with varying distances and resolutions. Images from each distance group are selected, resized to match the average sclera radius, and aligned by extracting a square region around the sclera center. This methodology enables the evaluation of periocular features extracted from CNNs and ViTs, as well as traditional handcrafted features, providing insights into their effectiveness for biometric identification. The verification results of various CNN and ViT layers with different vector normalization techniques reveal that averaging feature vectors across channels or patches reduces recognition accuracy, indicating this method is ineffective. Among the other 3 normalization techniques, L2 normalization per channel yields the best accuracy, particularly with CNNs. A comparative table is presented, showcasing verification results of traditional systems, the best layer of each CNN, and the best layer of each ViT. The top-performing CNNs and ViTs in the experiments are highlighted in bold, along with their parameters and layer involvement. This data underscores the importance of selecting appropriate normalization techniques for optimizing model performance in image recognition tasks. A comparative analysis of the performance of CNNs and vision transformers, ViTs, in a fusion task, utilizing L2 normalization per channel, reveals that this normalization method yields the best absolute performance for both network types. For CNNs, specifically ResNet models, the best performance is achieved towards the end of the network. ResNet 50 and ResNet 101 exhibit local minima at similar depths, which can be attributed to their comparable learnable parameters up to a certain layer. ResNet 50 provides the highest accuracy with an equal error rate, EER, of 8.53%, followed closely by ResNet 18 with an EER of 9.23%. In contrast, the best performance of vision transformers occurs in the first half of the network, with an EER curve displaying a U-shape that decreases to a minimum at layers 5667 out of 140. This suggests that ViTs achieve sufficient abstraction earlier in the network, and deeper layers may degrade performance. The learnable parameters of the networks are also discussed, with the tiny ViT model having only 1.33 m parameters yet achieving performance similar to the small and base ViT models. This indicates that the depth of the network does not necessarily correlate with better performance in this fusion task. The fusion results of selected CNN layers against all ViT layers are presented in Figure 6, showing that the tiny ViT model performs best, highlighting the impressive capabilities of ViTs and indicating that larger models are unnecessary. The study also explores the complementarity between CNN and ViT features through fusion experiments involving all possible combinations of CNN and ViT layers. The results, shown in Figure 5 and Table 3, reveal that the best fusion cases usually involve the optimal CNN layers or those nearby, corresponding to the oscillatory EER minima at the end of CNNs. The EER values in Table 3 demonstrate that the fusion of CNN plus ViT improves performance in all cases, with the best fusion combination being R50 CNN plus base ViT, achieving an EER of 7.72%. The fusion of R18 with ViTs shows an EER only 0.6% worse, at 8.32%. Additionally, another dark region in the early layers of both CNN and ViTs is observed, suggesting the possibility of finding another layer combination with good performance but fewer parameters. This could be useful in mobile biometrics where computing and storage are limited. By manually searching for local minima in these regions, a best EER of 8.79% is found using only 1.03 m parameters, which is approximately 1% worse than the absolute minimum but requires substantially fewer parameters. Finally, the incorporation of traditional features from section IIB further improves performance in all cases, with the combined performance of these traditional features falling between the CNNs and the ViTs. The application of pre-trained models, specifically CNNs and ViTs, for periocular recognition is discussed in the paper. It highlights the effectiveness of using these models without the need for training them for the task. The comparison between CNNs, R18, R50, and R101, and ViTs, tiny, small, and base, shows that CNNs typically require nearly the entire network depth for optimal performance, whereas ViTs achieve close to optimal performance at just 30% depth. The study questions the optimality of the strategy used in many CNN architectures, involving averaging feature vectors across channels or patches. Future work includes analyzing the observed complementarity of the models by studying which parts of the ocular region they rely on and extending the research to other biometric modalities.